Hi and welcome back to chapter number 9 of this lecture series on CCNA Cybersecurity Operations with me, Joachim Kävrestad from the University of Skövde. In this chapter, which is divided into two different video recordings, we will talk about cryptography. More specifically, we'll start with an overview of cryptography, what it is, how we can assure integrity and authenticity, and how we can assure confidentiality using cryptographic techniques. And then in the second lecture part, we will talk a little bit more about public key infrastructure. Let's get right to it and start from the beginning. There are some elements of secure communication that we should know about, or properties rather, that we want to achieve. Where the first one is data confidentiality, which means that data should only be read by authorized parties. There should be no way for someone that is not allowed to read a document or a message to read that document or message. Another property is data integrity. Data integrity means that data should not be modified, and if data is modified, it should be possible to detect that it has been modified. And this is of course to ensure that no one can perform a man-in-the-middle attack and change the content of a message between two parties. And then we have origin authentication, and this is a property that we use to guarantee that data is actually from the sender that it appears to be from. So if we receive a message, we should be sure that the sender is actually who the sender claims to be, or who we believe the sender to be. And then finally we have data non-repudiation, which means that a sender should not be able to deny having sent a message. So we can use cryptology or cryptography to ensure those properties in different ways. So let's start with reviewing what cryptology actually is. So cryptology has been around for a very, very long time, from the old Greeks, and I would guess even before that. And it's the science of making and breaking codes. So it basically combines two different disciplines, where we first have cryptography, which is the development and use of codes, and cryptanalysis, which is the breaking of those codes. And it's usually common practice to have both disciplines work against each other to create good ciphers. So we have cryptography developing encryption algorithms and implementations of those algorithms, and then we have cryptanalysts that try to break them in order to find weaknesses that can be patched in order to make the crypto system even better. So let's start with reviewing encryption just a little bit. If you're completely new to security while you're watching this video series, you may not heard too much about encryption. So when we discuss encryption or cryptography, we usually apply a little bit of math, or at least we represent algorithms in a way that looks very mathematical. But I'm going to try to keep it as brief as possible. So I promise you that you don't have to count anything. So we have some constants, or we have some variables that we need to be aware of. The plain text, which is the message or the body of data that we want to encrypt in its unencrypted form. We usually denote the plain text as P. And then we have the ciphertext, and the ciphertext is the encrypted, unreadable version of a plain text, and we usually denote this C. Finally, we have K, or the key, which is the key that is used in the encryption and decryption process to produce either the ciphertext or a plain text. So if we want to simplify as much as we can, encryption is the process of taking a plain text, applying the key, and we will use some algorithm to get a ciphertext, and decryption is the other way around. We have the ciphertext and we take the key to generate the plain text back. So K is commonly, K in this sense is not necessarily the password, it's a key of bits that is commonly computed using a key derivation function, or KDE, so that the value of the key derivation function for a given password will result in the key that we use in our encryption algorithm. We also have hashing, which is another cryptographic function, and hashing is basically a one-way function that takes any given plain text and produces a fixed value output. So it takes a plain text and produces a ciphertext or a hash digest or a data fingerprint or whatever you like to call it. There are so many names for this little guy. So as I said, ciphers, the algorithms. Ciphers used in old times. So we have the Caesarean cipher, which is a Roman old cipher, as one example. We also have the Enigma machine, which was quite a complicated cipher at the time, used by the Germans during the Second World War. And if we want to group the ciphers together, we can say that we have three different cipher types, where the first is substitution or disposition cipher, and this is the Caesarean cipher is an example of this. It's basically a cipher where you switch characters X stages in the alphabet. So if the key is 1, A becomes B, B becomes C, and so on and so forth. If the key is 2, then A becomes C, and then it's too hard for me to calculate any longer. Then we have transposition ciphers, and using transposition, letters are rearranged rather than changed. So you take the letters that are in the plain text and you scramble them according to some plan, and then you have a transposition cipher. And then we have polyalphabetic ciphers, and those are based on substitution but use different substitution alphabets. So it's not the same substitution pattern throughout the entire ciphertext. So changing into cryptanalysis, the art of breaking codes, it includes many different practices, and I've just wanted to list a few ways you can use to break codes, where we have first the brute force, which is essentially to try every possible key until we get the correct one. There is actually a property in most encryption schemes that makes it so that if you try to decrypt any ciphertext using an incorrect key, then you will actually get a mathematical constant back, and that makes for a scenario where you can actually be sure that if you get something else than that constant back, then you have the correct key. So brute force is about trying every possible key until you get the plain text back. Then we have the ciphertext, which is trying to get a mass of different ciphertexts and try to find patterns in them and see if you can find any common denominators or patterns or repeats, anything like that, and you can use that to break the crypto. Then we have known plaintext, which leverages some knowledge about the plaintext corresponding to a ciphertext. So you may have a ciphertext and you have a partial plaintext of that ciphertext, or you know the length of the plaintext or something like that. Then we have the chosen plaintext, and the chosen plaintext attack is that we choose a plaintext and we observe what the resulting ciphertext will be. And this is of course only possible if we have the ability to choose a plaintext and observe the output ciphertext. Then we have the other way around, which is a chosen ciphertext attack, and in this case we use different ciphertexts and observe the decrypted plaintexts. And then we have a meet in the middle attack, where we know a portion of the plaintext and the corresponding ciphertext, and we try to go from there and decipher how the crypt system works. So a fundamental property of modern day encryption algorithms is that they should be secure even if they are open. So in history we've used encryption algorithms where we rely on that the encryption algorithm itself is kept secure. But in modern day computing, we assume that the encryption algorithm is known to everyone and it should be secure anyway. And to be able to do this, we need two properties. First of all, there cannot be any way to get the plain text from the cipher. So if someone gets the cipher, they cannot revert that to the plaintext without the key, even if they know everything about the algorithm. And then we also need a property that incorrect key guesses should not reveal anything about the actual key, because we have the ability to test, well, many different keys, and if any incorrect key reveals something little about the actual key, then we will eventually decipher the whole key using this process. However, no single algorithm can be secure against key or password guessing attacks. Key or password guessing attacks means that we test all possible keys, and that will always work. It's just a matter of time. And we can, instead of trying the key, we can try the passwords instead, and we try all possible passwords, and the rules are the same. It will always work. It's just a matter of time, because if we have a large enough key space, we have enough the entire space of possible keys is so large that it's impossible to deplete even a few percents of it in any reasonable amount of time. That then we can be sort of secure against those guessing attacks. So there are two terms we need to know before the next slide, and those are key length, that is the size of the key in bits, and then we have the key space, which is the number of different possible keys given the key length. And if we look at some example, I just want to show you how the key space is important. So if we have a key length of 2 bits, that gives for 4 different combinations, so we can only have 4 different keys. If we have a key length of 3, then we have 8 different combinations. A length of 4 gives 16 combinations, so it's binary, so it doubles as we increase the key length by 1. If we have a key length of 40, then, well, you can see how many possible keys we can have and the size of the key space. And I want to tell you that this is not that many. You should try to go for a key space of at least 256 bits, preferably even more, depending of course on the security of your application. So this is a good time. You should know that the longer the keys, usually the more complex the math and the more time consuming is the encryption and decryption process. So of course it's reasonable to apply time as a factor in the key length selection process. If you have something that needs to be encrypted for only a few seconds, then you can of course have a lower key space than if you have something that needs to be encrypted for years. Then you have to have a much larger key space. I also want to tell you that key space and password space are not the same. The key, which is a binary key, is derived from the password. And the password space is much more variable. When we use a specific encryption scheme, we usually have a fixed key space. The password space is more variable and depends on password length, password complexity, stuff like that. So let's go into hash functions. I'm going to try to speed up or this lecture will be very long. So hashes are used to verify and ensure data integrity, and they are one-way functions, meaning that you take some arbitrary size data, you push it through a one-way function, and it produces a fixed length output. So that's the idea with a hash function. A hash function should provide hold two properties to be considered good. First, it must be irreversible. So even if you have the hash value or the hash digest, the output of the hash function, there should be no way to revert that back into the original data, even if you have access to the hash function. It should also be collision resistant, meaning that for any given input value, it should produce a unique output value. So those are the two major properties that a hash function should hold. And I will get into some example of why that is important a little bit later. So if we want to look at it, what happened now? If we want to look at it a little bit more formally, my mic is dropping. How interesting. So I'm going to try to sit down. So the hash operation, or the equation for a hash, is that the hash value is the value of the hash function for a given input x. So the properties it should hold is that the input can be any length, the output is fixed length. It should be relatively easy to calculate the hash function for any given x value. It must be one way and irreversible, and it should be collision free, so that two or more different x cannot result in the same h value. And a way that you use hash values is for storing of accounts or account data like passwords. And what you do here is that whenever a user creates a username and a password, you run the password through the hashing algorithm, and then you store the hash digest for that password. And the idea here is that even if an attacker manages to steal the user database, he will only have username and hash values, but it should be no way for him or her to get the passwords. And the logon process in this case is that whenever the user tries to log in, he will submit his password. The password will run through the hashing algorithm, and the hash will be computed, and the hash will be checked against the hash stored in the database. And since the hash value or the hash algorithm will always produce the same output for a given input value, then you can be sure that if the hashes are the same, then the password was correct. The problem here is if we have a hash algorithm that is not collision resistant, but many different input values will result in the same hash value, well, in that case, many different passwords will result in the same password hash, and many different passwords will actually work as a correct password. You can also try to use hashing, or use hashing in some sense in message verification. The way you do it here is that if you want to send a message between two parties, then you take the message, you run it through a hash function, and you apply or append the resulting hash value to the message. You send the message along its way, and the idea here is that the recipient will also take the message, autonomously compute a hash value for it, and then see if the hash values match. So if an attacker are to intercept the message, like in this case, Eve is intercepting this message and alter the number here from $30 to $30,000, well, then when Bob finally computes the hash value of the message, he will see that the hashes does not match, and thus he can know that the message has been altered in transit. The problem here is that this will not really work in practice because there is nothing stopping Eve from seeing what hash algorithm that is used and recompute the hash for the new message, and then Bob will think that the message is authentic even if it isn't, but we'll get back to that. So some well-known hash functions are first MD5, that was developed by Ron Rivest and is very well used. It produces a 128-bit hash value, and it should be considered legacy and should be avoided as long as you can. And that is essentially because this 128-bit hash value, that's not a large enough key space for it to be collision resistant. Then we have SHA-1, developed by NIST and creates a 160-bit hash value. This has known flaws, so you shouldn't use that. What you should use is SHA-2, which is also developed by NIST, and it comes in many different versions where the number at the end of the SHA name tells you how large the hash value will be. And of course, the bigger the hash value, the better, because the more collision resistance you get. So let's talk about what the hash will not do. So the hash value is there to detect accidental message changes or corruptions, stuff like that. There is nothing stopping an attacker from modifying a message and recalculating the hash. Also, there is nothing in the hash value that will verify who the sender actually is. So to get by those issues, we can use hash message authentication code, or HMAC. And what it does is that it adds an additional secret key as input to the hash function to ensure that the message is not altered in transit. So in this case, a key and the plain text is inputted to the hash function, and then you would need the key to recalculate the hash. The problem here is, of course, that this requires a pre-shared secret key. And we will get into how you overcome that obstacle in a little while, or perhaps in the next recording. So if we dig even deeper into encryption, we basically have two classes of encryption: symmetric encryption and asymmetric encryption. Symmetric encryption uses the same key for encryption and decryption, and it can use kind of short keys. It's faster than the other flavor of encryption, which is asymmetric encryption, and it's commonly used to encrypt bulk data such as VPN traffic, large data quantities, and stuff like that. Then we can the other way to do encryption is using asymmetric encryption, and in this case we use different keys for encryption and decryption, and this requires us to be able to generate a key pair with two keys that correspond to each other mathematically. This requires us to have longer keys, making the encryption algorithm rather slow, and therefore it's mainly used for quick transactions such as HTTPS or key exchanges. So what I will get to is that you commonly use asymmetric keys to share symmetric keys, so that you can use symmetric encryption for actual data encryption. So symmetric encryption relies on pre-shared keys. Both parties of a symmetric encryption communication have to have the same key. There are two different types of symmetric ciphers, block ciphers and stream ciphers. Block ciphers encrypt data in blocks of usually 64 or 128 bits, and stream ciphers encrypt bits one by one. The algorithms for symmetric encryption includes DES and triple DES, AES, SEAL, reverse ciphers, and a bunch more. So if we go into asymmetric encryption, using asymmetric encryption, each party will have to generate a key pair. So if you want to communicate with another person, both of you need to generate a key pair. And the key pair consists of a private key that is used for decryption and a public key that is used for encryption. And the idea is that data encrypted with a public key X can only be decrypted with a corresponding private key X. So if someone wants to send me encrypted data, he uses my public key to encrypt the data, and then the only key that can decrypt that data is my private key, and that is the key that I keep safe. So this solves the pre-shared secret problem, because I can willingly spread out my public key, but this method of encryption is very resource intense, because the keys are longer and the algorithms are more complex. So a practical solution is that we need to use the best of both worlds. So we usually use asymmetric encryption to share keys that we use for symmetric encryption. And then we use the symmetric encryption for the actual communications. And this also enables us to use temporary and fully random keys. So when we set up a session, in essence, we have one party, or we have both the parties generate a part of the symmetric key, and then we share the part that we generated, and we combine them into one symmetric key. And we, of course, use asymmetric encryption when we transmit the symmetric key parts. So how this works in essence is that if Alice and Bob wants to communicate, each of them will generate a public key, private key pair, and then they will send over the public key to the other party. So eventually both parties will have their private key, their public key, and the opposing party's public key as well. Then they can generate a symmetric encryption key and encrypt it using the other side's public key, send it over the internet, and the other side can decrypt the symmetric encryption key, and then they can use symmetric encryption for communication. There are, of course, some challenges in this, which we will get into in the next lecture recording. So, to sum up asymmetric encryption, it can be used for confidentiality. So, if data is encrypted using the public key, then it can only be decrypted using the corresponding private key. So, if someone wants to send encrypted data to me, they will use my public key for encryption, and then they will use, and I will use my private key for decryption. It can also be used for message authentication. And in this case, you do it the other way around, because you can actually encrypt data using the private key, and that data can then be decrypted using the public key. This doesn't add much confidentiality, because anyone can have access to my public key, but it will add message authentication, because anyone that if I send a package to anyone that I encrypted with my private key, they can, by decrypting it with my public key, be sure that it comes from me. You can combine the two to also get some integrity, and I think we will discuss that in the next video lecture. Otherwise, you'll have to read on it about it in the material. I'm sorry if the sound went a little bit bad midway through the lecture. I had some mic drop action in the recording room, but I hope we can stay on good terms anyway. I will do some setup to my recording room here, and I will see you next time where we finish off the cryptography chapter. As always, feel free to leave questions in the comment field if you have any.